Okay, folks, we're going to take a walk through the Earth CD's Metamorphic Rock section. And that's found under Earth Materials. That's the last of the rock types. This unit is shorter than the other ones. Again, the two main processes that change existing rock into metamorphic rock are heat and pressure. You need pressure to turn sediment into sedimentary rock, but we're talking about more extreme pressure and normally the addition of heat as well, and that will transform the rock and make it something different than it was initially. So, for example, here is a metamorphic rock called gneiss, and you can see that all of the minerals here are aligned, kind of like in parallel lines. This is what it would have looked like is a granite. I mean, it's more like a diorite. It's all black and white. But the heat and pressure will cause the minerals to realign. It'll be compressed along the sides, and all the minerals will realign, um, to conform with the stress. Here is the metamorphic rock slate, and it started its life as shale. Shale is just compacted mud, but if you bury that shale deep enough and you pressurize it and also add heat, it kind of acts like clay that's been fired in a kiln. It'll go from being like a very weak ceramic to being a very, very hard rock. And slate is way harder than shale. The shale you can almost break off with your bare hands, but the slate is extremely tough. The slate is what's used in pool tables, right? Uh, like it breaks off in big slabs. It's very durable and it's level. It's also used for floor tiles and sometimes to tile roofs. Here's another metamorphic rock called mica schist, and let's see here now. So that's what happens if you bury that slate even deeper in the earth. The clay minerals in the slate will recrystallize into mica flakes. That actually makes it weaker, so it goes from being a strong metamorphic rock to a weaker one. The mica schist, all of those mica flakes will come off if you scratch it. It's quite flaky. And these are the three agents here of metamorphism that transform existing rocks into something else. Heat, pressure, obvious. Chemically active fluids. Deep underground, we have there's water in the crust, and that water can be very, very hot. And because it's so hot and it's under so much pressure, it has a huge ability to hold ions in solution and to transport them from one place to the other where they can cause chemical reactions. So this speeds up the chemical changes that occur in during the metamorphic process. So the combination of all three of these that transforms rock from sedimentary or igneous into a metamorphic, or metamorphic into an even more metamorphic rock. So heat is going to speed up chemical reactions. Um, Here we have a particular kind of metamorphism called contact metamorphism. Inside the crust, when you have magma chambers like this, or it could be lava flows on the surface, the rock that extreme heat comes in contact with can be baked and metamorphosed. You don't need any pressure. It's just the inclusion of heat. It's not enough to melt it, but it will transform it. So we have contact metamorphism on the periphery, on the edges of igneous intrusions and also lava flows. So that's contact metamorphism. And here you see there's a little a little video here to illustrate the point. This, by the way, is a convergent plate boundary where one plate is being driven underneath another one. It produces mountain chains. It produces magma, right? So you have these igneous intrusions. You also have volcanism when that magma reaches the surface. Most of it does not, but some of it does. Here's a close-up of contact metamorphism. It would be in this zone right next to the magma. Inside here, these are inclusions. These are pieces of the existing rock that have broken off and got folded into the magma, and these are pieces of this rock up here. But then all along this edge, we have this zone of contact metamorphism that's come into contact with the extreme heat of the magma chamber. The temperatures increase with depth, the pressure increases with depth, so great depth is going to create more metamorphism. Not much of an animation there. And so the pressure tends to reduce the volume, increase the density, maybe like change the mineral arrangement to correspond to the direction of stress. And that can also fold up the strata. If you see folded sedimentary rock, um, that can be one of the indications of metamorphism as well. Chemically active fluids, they're going to speed up chemical reactions that take place inside the crust and allow new minerals to form. Maybe minerals can be removed, other minerals can be generated through all these chemical reactions. And here's the texture of metamorphic rocks is, well, I can tell you what these are. This is a schist with garnet crystals embedded in it. Those garnets can only form at very, very great depths. A lot of pressure, high heat, garnets will only form in those locations. This is a gneiss. This may have been a granite, or it could have been a shale that was so metamorphosed that all of the minerals lined up in these kind of like parallel and sometimes like curvy lines. We call that pattern foliation, when you can actually see like layering inside a metamorphic rock. This down here is a third form of the metamorphism of shale. It occurs between slate and schist, and this wasn't discussed earlier. We have shale, then slate, then this is called phyllite. It's an intermediate form between slate and schist, where it's all microscopic. They're very, very tiny microflakes. It's enough to make the rock shiny, um, but it doesn't flake off in the same way that schist does. And this one here, this is a metamorphosed red sandstone called quartzite. When a quartz sandstone is metamorphosed, all of the quartz grains basically fuse together, and here there's some iron oxide as well. That's probably what the cement was, and it turns into the rock quartzite, which is it's actually the hardest rock that exists. We have our low-grade metamorphism from a shale, which is a sedimentary rock, just compacted mud, into the slate, which is a hard, dense, tough metamorphic rock. And then so here we have slate, phyllite, and schist. The phyllite derives from the same word as phyllo-pastry. That's what flaky is made of, is phyllo-pastry, or a croissant. And so phyllite is derived from the same word, slate, phyllite, schist. And this is deeper inside the earth, higher temperatures and pressures. Here's a granite that when it's put under differential stress, in other words, it's being squeezed from the sides, and really, if this were drawn properly, this would be very narrow and very long, because the granite, well, rocks deep underground, once you go below about a kilometer, the rocks will become plasticky, and they can deform and stretch without melting. So this granite will actually behave almost like a silly putty, and it will it'll stretch, it'll get longer this way, just like if you're squeezing silly putty, it'll get longer this way, and it'll get narrower this way. So it's, I kind of don't like this, the way that they have it represented here. It seems like the minerals are just changing orientation, but the entire rock is being stretched like this. It's getting very long and it's getting narrow. You can't see that in this diagram, unfortunately. So here we go. There's your gneiss. A gneiss can form from the metamorphism of shale, which goes through the various stages and then ends up as a gneiss, or it can go directly from a granite. You end up in the same place. We call this pattern when we have banding, banding in metamorphic rocks. It's called foliation. So folding, foliation, um, it's the bands that you see in some metamorphic rocks. Some don't have it, some do. Here's a non-foliated metamorphic rock that's quartzite. Quartzite used to be sandstone. Huh, it doesn't happen that fast. But there you go. All of the quartz grains are fused together, and it turns into just like a big lump of quartz. Um, you can have new minerals forming because of the hot water that's circulating around inside the crust. Read into this stuff later on in the course. Vein deposits. Oh, look, a quiz! Fantastic. So we have to guess what kind of rock this is. Oh, look, we see garnet crystals. Oh, garnet mica schist. I'd say that's a pretty good guess. Garnet mica schist. So this is a schist made of mica flakes that has garnets embedded in it. Ooh, look at that. That looks like a metamorphosed diorite. All of the minerals have been aligned parallel. That's a nice. Here is a pretty small on the screen here. I believe that's just a regular old mica schist. Don't see any garnets in it, so it's just a regular old mica schist. This is the one that I told you kind of looks like a flaky. That's phyllite, tiny mica flakes, the intermediate stage between slate and schist. And then finally, we have this rock. That's the first stage in the formation of shale. The pool tables are made out of floor tiles, slate. And here is oh look, there's another one. These are non-foliated metamorphic rocks. That is a very hard, oh look, we can check it with acid. No reaction, so it's not made of calcium carbonate. We can scratch it on glass. It can't scratch the glass, so it's not made of quartz. Well, it's anthracite coal. It's the metamorphic version of coal. Here we have, let's try the acid. Oh, there's a reaction. You know what that means? That's right, it's made of calcium carbonate. Calcium carbonate reacts with acid, and therefore it must be a metamorphosed limestone, which is marble. I don't know if marble has occurred in this yet. Oh, let's see if it scratches glass. No, no scratch. Marble is too soft to scratch glass, but it will react with acid because it's made of calcium carbonate. Quartzite is the metamorphic equivalent of quartz sandstone. Marble is the metamorphic equivalent of limestone. We can have a metamorphic conglomerate. I think you're going to see a picture here now in a second. This is the metamorphosed sandstone. Let's try the acid. Nothing. This is not made of calcium carbonate. Scratch on glass. Yep, scratches the glass. We know it's made of quartz. Well, it's like a little mini lab here, a virtual lab. And then the very last one, this is what a conglomerate looks like if it's subjected to heat and pressure, and it turns into a kind of a plastic. Almost like if this were made of silly putty. It actually like stretches without breaking, without melting. That's a stretched pebble conglomerate. Let's try the acid. No reaction. Glass. Yeah, I'll tell you why it scratches. Because these pebbles are probably made of quartz. That's what you would assume. So there's your stretched up, and there you go. And folks, that